Hello everyone. In this video we are going to begin to expand on our study of one-dimensional motion. Up until this point we've looked quite extensively at constant one-dimensional motion, constant velocity, and uniformly accelerated one-dimensional motion with our friends the kinematic equations. But what if the motion is a little bit more complex? So here's an example I want to go through. This is one that if you are in calculus right now, might be a little ahead of where you are, but soon you'll be doing this kind of thing quite a bit. If you've already had a year of calculus, it'll be a review, and just kind of bear with me as we build. So here we have a lab with a disk rolling down a hill. And let's say the position versus time function worked out to be x for position, of course, equals 2 meters per second squared, t squared. And I want to know what is the velocity as a function of time. I want to know what's the velocity as a function of time here, okay? And I don't have some kinematic equation to plug stuff into to use. So let's graph this first of all. Here's a graph of position in meters versus time in seconds. Since it's time squared, this of course would be a parabola, a top opening parabola. Well, if you remember when we talked about this kind of thing last year, if we wanted to know, let's say, the velocity, the slope of the position time graph, at some time t, so right here, right, want to know the slope of that graph when it's a curve, the way that we discussed it last year was to pick a second point, say here, which I'm going to now say in a very calculus-y way, is at a time t plus delta t. So delta t being the extra bit of time between these two, if you will, right? So that's time t plus delta t. We could then draw a chord between those 2 points. And we could, of course, find the slope of that chord as rise over run. Right? The rise would be the change in the position, since position's on the vertical axis, and the run would be the change in the time. So the slope of this chord would be the change in the position over the change in the time. Hopefully, you're sitting out there saying, wait, we know what that is. Right? The change in the position over the change in the time is what we called average velocity. And in fact, last year we actually defined the average velocity with a math model, but we also defined it to be on a graph the slope of a line connecting any 2 points on a position time graph. So this is no different than kind of what we did last year. But if you remember then, we talked about, well, that's just an average between these 2 times. What could we do with this second point if we wanted to be closer to finding the velocity, the slope of the graph, at this time? You might remember we said, well, we could bring it closer. And that would give a better average. Draw a chord between those 2 points and bring it closer. And we get a better average and closer and closer. And when you shrunk those points down to where they were just infinitesimally apart, you get the tangent line. And the slope of the tangent line is the slope of the curve at that point. And in math language, what we are doing there is finding the instantaneous velocity. Notice no extra little line, which means average, which is, in math, taking the limit as the time interval shrinks to 0, delta t, right, shrinks to 0, of our average velocity, our displacement over time. Now, last year, I kind of showed you how to find slopes of tangent lines on your TI calculator. We picked a bunch of different times. Right? We found the slopes at those times, the velocities at those times, and then we made a velocity time graph, and we kind of built our kinematic equations from that. But what if this is more complex? What if we want to actually do the calc here? Right? Well, I'm going to take you through one and only one example of how to actually do a limit. Again, you're going to spend a lot of time in calculus doing limits in the next probably month or so. All right, you'll do a lot of limits. So just bear with me here if you haven't done these yet. You know, this will get easier as you learn about it more in calc. So, this is, of course, again, the instantaneous velocity. Right? And that's because of this. Because we're going to shrink the time interval down to 0. We're going to shrink those points closer and closer and closer together to find the slope of the tangent line. So, change in position is, of course, final minus initial position. But what is the final and the initial position? Well, in this case, we've got a function up here, right? So the final position is the position at time plus delta time, t plus delta t. The initial position is the position at t. This is function notation here, folks, right? Function notation for a moment. Final position is the position at t plus delta t. The initial position is the position at t. Well, if we plug that in to our position function that we have up here, we can see that the position at a time t would just be 2t squared. Now, I'm getting rid of the units here just to make life easy. We'll put them back in at the end. But our position at a time t plus delta t would be 2 times t plus delta t quantity squared. See where I got that? So if my time is t plus delta t, I'm just plugging it in for that t. So we need to plug those two things in. Now, if you're taking notes, feel free to, pause, write stuff down, go backwards and forwards within the PowerPoint. So if we plug those in, we get this. We now have the instantaneous velocity as the limit as delta t approaches 0 of the quantity 2 times t plus delta t squared minus 2t squared all over delta t. Well, let's square this term out. Right? FOIL it, if you will. Multiply by 2. All right, so we get t squared times 2. We get 2t times delta t times 2. Makes it 4t times delta t. And then we get delta t squared times 2, which is 2 delta t squared. And then don't forget, we still have the minus 2t squared running around over here. If you're not sure where I got all this, go ahead and write some extra steps, right? And square this out and FOIL it and then multiply by 2, and you'll get this. Notice we've got a 2t squared here, and we've got a minus 2t squared there, which of course cancel out. Leaves us with this. But then notice the delta t on the bottom cancels out with this delta t here, and with one of the squared delta t's there. Leaving us with an instantaneous velocity, which is the limit as delta t approaches 0, of 4t plus 2 delta t. So now's when we're going to actually do the calculus, which is we're going to take the limit. We're going to evaluate this function as delta t shrinks to 0. Well, as delta t shrinks to 0, 2 times something which shrinks to 0 is essentially 0. And so what we're left with is the instantaneous velocity is 4t, where 4 has these units on it of meters per second squared. So look at that. If you're taking notes, especially if you're in, first year calc, this might be the first time you've seen it, or again, this is something you're going to do with a lot of functions, all right? Just kind of look at the process of what we're doing here, right? We are trying to find the slopes of all the tangent lines, an actual function. So rather than finding the slope of a tangent line at a particular time and then at another time and another time and another time, we're doing some calculus here in order to figure out the entire velocity function. This is a much more powerful thing than we did last year, okay, which is why we need the calculus. This is calculus. Okay. Now look at this function that we got for the instantaneous velocity. It's a function of time t, not t squared or square root of t. Right? So hopefully you're looking at this and saying, oh, that's a straight line, y equals mx plus y-intercept of 0. So a linear graph with a y-intercept of 0 for the velocity time graph. Now, velocity time graphs, of course, have slopes, which are, or is, the acceleration. And if we look at this function, right, we can see that the slope should be that, right, 4 meters per second squared. So notice we found the acceleration here by pulling it out of our velocity time graph. But we have something more than just a single velocity, a single slope at time t. We've got all of the velocities, right, at any time t. We just have to evaluate it. Again, this is the power of doing calculus, okay, as opposed to trying to do this analytically or numerically or something like that. Right? This is what Newton and Leibniz created, right, that allow us to do more complex functions. We're going to do some more examples as we go here, but I'm not going to write them out this way in the big limit form, okay? That's what we're doing always. Always remember what this is. We are finding all of the slopes to our function, whatever our function is, whatever we're looking at, right? By taking a second point, making it closer and closer and closer together, shrinking that interval in between. What we just did has a fancy name in calculus. It's called a derivative. In fact, this is pretty much what you do in first semester calc. You learn how to do derivatives of more and more and more complex functions. Okay, we're going to stick with a fairly routine set of functions in here, especially first semester. Okay, but you'll get way past that. I mean, by the end of first semester, the stuff we're going to do in the next few days here will look simple to you. I know it's going to be tough now, and you're going to have to follow through, ask some questions, right? But we'll get there. So the derivative is technically defined as the instantaneous rate of change of one variable with respect to another. It's a slope, right? All slopes are rates of change. How fast does one variable change when you change the other variable? Right? So every slope is a derivative. Every derivative is a slope. And if you remember that, right, you'll have learned something from physics that'll help you understand what you're doing in first semester calc. Now, this is actually Leibniz's notation for how to write a derivative. You see these D's, all right? So you write this as the derivative of the position with respect to time. That's the way this would be read. Okay, so writing this in symbols is the instantaneous velocity is the derivative of the position with respect to time. This is some notation. There are other ways of writing this that you'll learn in calc. There's Newtonian notation, but conventionally we tend to use Leibniz's notation, which use these little d's, okay, to show as a derivative. Okay, so this is kind of how we write velocity. Velocity, another way of looking at this is velocity is the slope of the position time graph. Every slope is a derivative. Now, we could spend days and weeks, which you will in calc, figuring out how to take the limits of functions, right? But as you saw, this can get quite complex. I mean, imagine a function that's, t cubed and square roots of t's and all sorts of funky things, right? You're going to have to, spend a lot of time doing that t, evaluating it at t and evaluating it at t plus delta t, and then doing a ton of algebra inside of the limit. There's all sorts of tricks you'll learn in calc for doing that. What I'm going to do right now is actually teach you the rules for derivatives. I'm not going to derive them, although I'll try to explain why they work the way they do. But, you're going to prove that to you, and it's going to be proved to you in calculus. That's why you have to at least take calc while you're taking this course. All right, so I'm going to teach you how to use a derivative, how to do a derivative. Calculus is going to derive them for you. So here are the rules. Anytime you see a b, an m, or an n, they're constants, right? They're just some number, okay? So our first rule is the most basic one, and hopefully after I explain it, it'll be fairly obvious. It's the constant rule. So let's say we have a function y equals b, where b is a constant. Notice there's no t in here, there's no x if we're doing it in math, right? There's nothing to change, it's just constant. So the derivative of the function y with respect to x is the derivative of b with respect to x, because y equals b. But b is a constant. Let's go back to our definition here that a derivative is a slope. Think about what this graph would look like. Y equals b. Right? It would be a horizontal line, right, is the graph of a constant. And what's the slope of a horizontal line? 0. Think about that, right? A derivative is a rate of change. So what's the rate of change of a constant? Nothing. Right? So hopefully that's a rule that you just kind of go, yeah, that makes sense, and we can use it. So anytime we're taking the derivative of a constant, it's just 0. There is no rate of change. This is a big one. It's called the power rule. We'll spend a lot of time in calc working with this one. So let's say we have a function y equals x to the n, where n is some number. Could be 2, like in our example, so it's x squared. It could be 1/2, and it's the square root of x. Right? Could be -2, which is actually 1 over x squared. I mean, it could be all sorts of things. How do we take the derivative? Well, the derivative of y with respect to x is the derivative of x to the n with respect to x. Again, you're going to derive this in calc, but here's the rule. It's n times x to the n minus 1. You multiply by the exponent and subtract 1 from the exponent. Keep that phraseology in mind because it'll help you do derivatives. You multiply by the exponent, subtract 1 from the exponent. We'll do some examples so you'll see what I mean here. Okay? But this is how you do anything that's an x to the n. Anything that's an x to the n. All right, you multiply by the exponent, subtract 1 from the exponent. A little more general, what if we have a constant times x to the n as our function? Well, derivatives kind of work like many things that we've seen in regular algebra, which is that you can factor out constants, right, when they're multiplied in. So we can distribute out, if you will, the b. So the derivative of y with respect to x is the derivative of b times x to the n with respect to x, which is the same as distributing out the b, which leaves us with b times the derivative of x to the n with respect to x. And we already know what the derivative of x to the n with respect to x is. It's the power rule. So it's just b times n times x to the n minus 1. Again, if you just remember, multiply by the exponent, multiply to the constant, right, to the coefficient, and then subtract 1 from the exponent. Multiply by the exponent, subtract 1 from the exponent. One more rule that I'm going to teach you right now, and that'll be good for us for a good semester before we need anything more complex, is something called the sum or difference. So let's say you have a function that has a sum or difference, like y equals x to the n plus or minus x to the m, where n and m are actually different variables. Because if they were the same variable, you could combine terms, right? They'd be like terms, you could put them together. If that was x squared plus x squared, you just write it as 2x squared. Right? So it's x to the n plus or minus x to the m. I'm going to have you watch a movie in a day or so, and they do a pretty nice job of explaining why it works this way. But basically, you can distribute through a derivative. In other words, you can take a derivative of each piece one at a time. The little saying is the derivative of a sum or a difference is the sum or the difference of the derivatives. The derivative of a sum or a difference is the sum or difference of the derivatives. So you can take each piece one at a time. Again, we're going to do some examples here that'll help you out, right? And we already know how to take the derivative of x to the n with respect to x, and we know how to take the derivative of x to the m with respect to x, because it's just the power rule. Right? So you get n x to the n minus 1, multiply by the exponent, subtract 1 from the exponent, plus or minus, depending on what the equation is, m times x to the m minus 1. Multiply by the exponent, subtract 1 from the exponent. So with these 4 rules, you're going to be able to do any derivative I'm going to give you in first semester. All right? When we need more rules, we'll learn them then. You'll learn more rules for things like, products and quotients and trig functions and all sorts of things in calculus. Right? But we don't need all that right now. All right? We tend to stick with, I don't want to say simple, but a little more basic kind of functions when we're doing one-dimensional motion. So let's do some examples. First off, the example we did the long way by actually taking the limit as delta t approaches 0. What could we do is, now that we know the full-on calculus with this? Well, since velocity is the slope of the position time graph, velocity is simply the derivative of the position with respect to time. And we have a function where the position is 2t squared. So, if we use the general power rule here, remember this one? We multiply by the exponent, subtract 1 from the exponent. The exponent is a 2. So we multiply by 2, and we subtract 1 from 2. Everybody see that? Took the exponent, multiplied by 2, subtract 1 from 2. Well, 2 times 2 is, of course, 4. 2 minus 1 is 1. So we get 4 meters per second squared from here, t. That's that whole long limiting thing we did in literal seconds if you know the rules of calculus. This is what makes it so powerful to know how to do differential calculus, which is what we're doing now, fancy term, differential calculus. Right? Once you know, those people that have had a year of calc already, right, look at this function and they can pretty much instantly tell you what the velocity function would be, right, just by doing a quick derivative. And you will get there if you are in first semester calc. You will get there. Okay? Right now, you got to work the rules, right, as your examples. Now, once we know the velocity function, all we got to do is evaluate it at any time, and we know what the velocity is. So, we're going to do a bunch of examples here, okay? And in each case, I want to know the instantaneous velocity at 2 seconds. Right? Just at 2 seconds. Now, we could do this by, plugging the function into our calculator and telling it to find the tangent line at 2 seconds for each function, and it would take a second point and move the points closer and closer and closer and closer together till it was happy with the slope of the tangent line, and then it would tell you. Or we could just apply calc. So here's A. X equals t to the negative third, which could also be written, of course, as 1 over t to the third. Well, if we use the power rule here, the velocity is the derivative of the position with respect to time, so it is the derivative of t to the negative third with respect to time, and the power rule says multiply by the exponent, subtract 1 from the exponent. Multiply by negative 3, subtract 1 from negative 3. Be careful here, negative 3 minus 1 is not 2, it's a negative 4. Once we have the velocity function, finding a particular velocity is just as simple as plugging the numbers in and doing the algebra. So if we evaluate it at 2, right, we get to 2 sig figs, negative 0.19 meter per second. That means it's going to the left, right, at 0.19 meters per second at 2 seconds. But realize, anytime I asked you, you just plug it into the equation. It's a powerful little tool to have some basic calculus. Next example, x equals 14.05 meters. Well, hopefully you're looking at that and saying, oh, that's a constant, right? Notice there's no t in here anywhere. So as time goes on, you're just staying still. So what would your velocity be? Well, of course, hopefully you're saying it's 0, right? Because we're not moving. We're staying at the same position. But the rules of derivatives say the derivative of a constant with respect to time is, of course, 0. That's an easy one, I hope, right? Even if you don't remember the power rule, technically, right? There you go. Example C, a little more complex, 2.0 t to the fourth. Well, the velocity is the derivative of the position with respect to time, so the instantaneous velocity is the derivative of 2.0 t to the fourth with respect to time. General power rule, multiply by the exponent, subtract 1 from the exponent. So we multiply by 4, subtract 1 from 4. 2 times 4 is 8. 4 minus 1 is 3. We get 8 times t to the third. You want to know the velocity at some time? Plug in that time for t and solve. 2 to the third is 8. 8 times 8 is 64 meters per second. Look at how quickly we can do this without needing some TI calculator to do some numerical thing for us, right? If we know the calculus. All right, let's do a little more complex example now. Ooh, there's a bigger function. What if our position is given by 3t squared minus 4t plus 2? Well, it's still a parabola, but even so. What if our position is that function? Okay, well, if we want to find the velocity at 2 seconds, you can imagine here how much more difficult the limiting process would be, because you'd have to put in a t for each one of these for your initial, and then your final would be, you'd have to put in a t plus delta t here and a t plus delta t there, and then there's a lot more algebra, right? The calculus, pretty straightforward. The instantaneous velocity is the derivative of the position with respect to time, the slope of the position time graph. So it's the derivative of 3t squared minus 4t plus 2. So we're going to apply a couple of rules here. First off, here we have a difference and a sum. Right? And you remember the sum or difference rule. The derivative of a sum or a difference is the sum of the derivatives, or difference of the derivatives. So in other words, I'm going to take these one piece at a time. So the derivative of this whole function is the derivative of 3t squared with respect to time, minus the derivative of 4t with respect to time, plus the derivative of 2 with respect to time. Now, notice I got to carry this minus sign around here somewhere. I either have to put it here or I have to put it on the 4, right? I got to keep that negative there so I don't lose it. So let's look at these one at a time. First off, the derivative of 2 with respect to time, I hope you're saying to yourself, is 0, because it's a constant. It doesn't change. The derivative of 3t squared, multiply by the exponent, subtract 1 from the exponent. Now, you got to be a little careful here. This is technically t to the first power. So you're multiplying by 1, which doesn't change anything, and then subtracting 1. So here we have 3 times 2 is 6, t to the first power. Right? So it's 6t. But look at this one. This is t to the 1 minus 1, which is t to the 0. What's anything to the 0 power? 1. Right? So t to the 1 minus 1 is t to the 0 is 1. So this is 4 times 1, or 4. And our velocity function is 6t minus 4. That would be a straight line with a y-intercept at -4 and a slope of 6, right? Evaluated at 2 seconds, 6 times 2 is 12, minus 4 is 8 meters per second. Again, apply the rules here. Okay, apply the rules if you're new to this. Now, by the way, once you get good at this, right, it would really be nice to see maybe the first step to tell the reader what you're doing. The second step to tell again what you're taking the derivative of. And then if you can go from here to here and skip all these steps, by all means, feel free. Right? So as you get good at this, again, once you get done by the end of first semester, you're going to look at an equation like this and take its derivative and pretty much just look at it and go, oh, that's 6t to the first minus 4 plus 0, and I'm done. Right? But for now, if you're new to this, write your steps out. You'll see me write my steps out for you, or write some steps out at least on the key. All right, a bigger function. Now this one, I don't even know what it looks like graphically. I'd have to punch it in and look at it, right? It's a fairly complex function. X is 3t squared minus 4t plus 6t to the -4th plus 5. Now imagine doing this with that limiting process. This would take a while. Oh, you're going to do this kind of thing in calc, right? But the calculus makes it way simpler when you know the rules. So the velocity function is the derivative of the position with respect to time, which is the derivative of this big thing with respect to time. Sums and differences is the sum or difference of the derivatives. So in other words, we take each piece one at a time. In each case, well, in this case, that's the derivative of a constant, so it's 0. Each one of these, you multiply by the exponent, subtract 1 from the exponent. Multiply by the exponent, which is a 1, subtract 1 from the exponent. Multiply by the -4, subtract 1 from -4. Again, I'm writing out some steps, right? You can skip these if you know what you're doing. 3 times 2 is 6. T to the 2 minus 1 is t to the first. Don't forget the minus sign's got to come along for the ride. T to the 1 minus 1 is 0. T to the 0 is 1. Over here we get 6 times -4 is -24. -4 minus 1 is -5. So we get 6t minus 4 minus 24t to the -5th. And once you have this function, you can find the velocity at any time. Plug in a 2 for t. Don't lose the -5 up here. And you get about 7.3 meters per second. Notice how much more complex of a function we're looking at. And by the way, don't get lost in the calculus. These are one-dimensional motions. So that means this is an object going back and forth in a straight line, right? Doing something, going right, going left, doing different things at different times, speeding up, slowing down, right? But all in one dimension right here.